Hi everyone. Today we're going to talk about electric circuits and how Ohm's law works in terms of calculating what should happen in an electric circuit. So here is your basic cartoonish version of an electric circuit taken from one of my favorite types of Looney Tunes cartoons, the ones with Foghorn Leghorn. But anyway, some basics with circuits is that the only reason these things work is because there is something called an electric potential difference. So what electric potential is it's electric potential energy per unit charge. So you can kind of think, okay, back in when we were dealing with mechanics, we had things like gravitational potential energy, which was mgh at the approximation level at least, and you could consider a gravitational potential energy per unit mass. So just take mgh divided by m, and it's like, okay, that would be gh, so however much mass I put at a certain height, that tells you how much potential energy there is there. You can do the same thing with electric potential energy. You can come up with something called the electric potential. It's telling you, well, however much charge I put at that location, that tells you how much potential energy there is. But just as with gravity, where the only thing that was really different, that was really important, was differences in height, that is, differences in gravitational potential energy, well, just with circuits, the only thing that's actually important is differences in electric potential energy, and thus differences in electric potential. So it doesn't matter whether I'm touching one wire that is at 2 million volts and another wire that's at 2 million volts as well. Nothing's going to happen because the electric potential is the same with both wires, so no current is going to go from across me from one to the other. However, if I was touching one wire with 100,000 volts and another wire with 50,000 volts, that would be real bad because there's a potential difference of 50,000 volts, that is 100,000 minus 50,000, from one end of me to the other, and that makes it very probable that a substantial current is going to go through me. So when we say there's an electric potential difference of 12 volts, we often just say that there's, quote, a voltage of 12 volts. Just keep in mind that when you say, yep, there's 12, the voltage there is 12 volts, what people really mean is that the electric potential difference from one end to the other is 12 volts. It could be 0 volts at one end and 12 volts at the other end, or it could end up being 1,000,000 volts at one end and 1,000,012 volts at another end. So there's also the fact that when you do have these electric potential differences, that means that as charge goes across from one place to another, there is going to be work done. That work might be done by zapping you and killing you, or that work might be done by turning on a light bulb or something like that, getting it to shine. But the work done is equal to the charge times the electric potential difference going from one place to the other. Again, remember, voltage by definition is electric potential energy difference per unit charge. So you multiply the voltage by the charge, that'll tell you the electric potential energy difference, and thus the amount of work that's being done by the electric field when the charge goes from one end to the other, which is what happens whenever you plug something in, when you connect something to a battery, etc. A few more basics. In SI units, the unit of charge is called the coulomb. That's just the SI unit of charge. I'll tell you now, a coulomb is a whole lot of charge. If you got zapped with a coulomb of charge, you would die, and you would also probably take out a number of others around you. The electron and the proton have the smallest possible isolatable units of charge. They both have charge magnitudes of 1.6 times 10 to the minus 19 coulombs. So again, a coulomb is a whole lot of charge. So just divide 1 by 1.6 times 10 to the minus 19, and you realize that if something has a coulomb of charge, that means that it has about 6 times 10 to the 18, that is 6 quintillion elementary charges in excess that are ready to do their work. Now, another set of basic definitions is something called the ampere. The ampere, or often called the amp, is the amount of, it's 1 coulomb per second. Electric current, by definition, is the amount of charge that flows through a point in per unit time. It's the amount of charge per unit time. You can kind of see that in these units, 1 coulomb per second. That's what an amp is. It used to be that the coulomb was defined to be the amount of charge that went by a point in a circuit in 1 second with a current of 1 amp flowing through that circuit. That used to be the definition of the Coulomb, but now it's been redefined into something a little bit more abstract as of May 20th of 2019, but the idea is that it's still pretty similar to this. Now, keep in mind that it's not voltage that kills you, it's current that kills you. If you're wearing highly resistive gloves, then if you touch one wire with 2 million volts and the other wire with 1.5 million volts, that 500,000 volt potential difference is probably not going to kill you if you have highly resistant gloves on, because that means that there's not going to be much current that goes through you. It's the current that goes through you that kills you. Actually, more technically speaking, it's the amount of charge that goes through you that really has the potential to do that. Quick example, if you were to rub your feet across a carpet on a dry day and then touch the corner of one of the corners in your house, you would get zapped by the static electricity. It turns out that that's actually about 20,000 volts there, sometimes 40,000 volts, just depending on the day. And that's a big voltage, but it's a small amount of total charge. It's actually a rather large current, believe it or not. It's the type of current that normally would be expected to kill you, but it's for such a short period of time that it's pretty harmless. It might surprise you. If it's big enough, it might cause you to curse, but other than that, it's not going to do any harm. What can do harm? Well, here we're talking about a steady current. So if there's a steady current of 1/1000th of an amp, you'll start to feel that. And at about 2 to 5 milliamps, that is 2 to 5 thousandths of an amp, that's going to start to become painful. But between 10 and 20 milliamps, that's where your muscles start to become paralyzed. In other words, if that amount of current is going through you, you're not going to be able to do anything about it. In fact, at about 18 milliamps, chest muscles contract and your breathing will stop. And then finally at 100 milliamps, your heart is not going to pump anymore. So that would be bad. Now, I know that the defibrillators that they use to literally bring people back to life, as it's said in the medical community, when their heart stops and they have to be brought back to life, in quotes. Those are large fractions of an amp. I think they're something like 0.2 or 0.3 amps or something like that. But it's for a reasonably short period of time, but just long enough so that it can kind of kickstart your heart going again. Now, how does electric current relate to voltage? How that occurs is something called Ohm's law. Ohm's law is actually something that's not always true. It's only true for certain types of materials. We call those types of materials ohmic. I know that's extremely helpful when you realize the circularity of that. In other words, what we're really saying is that Ohm's law is true except when it's not. But anyway, what Ohm's law states is that the voltage is equal to the current times the resistance. That's how it's often remembered. You have this little mnemonic called like VIR, V-I-R, VIR, voltage equals current times resistance. Physically, that's not the best way of thinking about it, because it's actually, if you think about it, it's electric potential differences, that is voltages, that result in current. So if you're thinking about it from a cause and effect standpoint, what we really want to do is kind of think of this as rearranging this equation. We have the resulting current is equal to the voltage divided by the resistance. It's the same equation, just different cause and effect understanding. The units for resistance. Resistance tells you, well, the resistance to charge flow. Insulators have high resistance. Conductors have very low resistance. The units for resistance are ohms. The symbol for ohms is the capital Greek letter omega. Yeah, I know it looks like headphones, but that is the symbol for ohms. Capital Greek letter omega. Now, another equation to go, and don't worry, we're going to get plenty of practice using these equations very soon, is that the rate at which a resistor, or that is anything that has resistance in it, dissipates electric potential energy is known as power. A resistor can be anything. It could be a toaster oven. It could be a light bulb. Anything that has resistance and thus results in work being done when current flows through it. So that dissipates power. And the equation for the rate at which power is dissipated is, another mnemonic, PIV. P equals IV. The power dissipated by resistance is equal to the current flowing through it times the potential difference from one end of it to the other. So if you have 2 amps of household current flowing through a light bulb and the potential difference there is 120 volts, then that would mean that the power of that light bulb would be 240 watts. Well, that's a really big light bulb. Light bulbs usually are not able to do that. You can buy the ones that can, and then you can get really bright light bulbs in your house, but a 60-watt light bulb is more common. So that would be a power of 60 watts on the left side of the equation. And remember, household current is 120 volts. That's actually a number that you should memorize. Household current has a potential difference of 120 volts, roughly speaking. It actually oscillates between like 100 volts and 120 volts with an average of 110, but 120 is what we care about here. Anyway, so if it's a 60-watt light bulb, if you want to know how much current's going through that, you would say 60 watts equals current times 120 volts. So divide both sides by 120 volts, you would get a current of 0.5 amps flowing through that particular light bulb. Now, some symbols that we often get into when we're dealing with these circuits, and we're going to see a lot of these soon. The symbol for a resistor is kind of this back and forth zigzag type of thing, and a wire would just be a straight line going on from one end of this and then straight line going to the other. A voltage source, which might come from an electrical outlet, might come from a battery, might come from a generator or something like that. What you have is you have one line, and then parallel to that, and in the middle of it you have a second shorter line. And whether it's like this or doing that twice or 3 times or 4 times or whatever, it really doesn't matter. It just depends on the feeling of whoever is drawing your circuit diagram. So sometimes, though, instead of having, say, this being one end and this being the other end of the circuit, sometimes you'll have this kind of tornado type thing. What do these lines mean, though? Going back up here, the long line denotes the positive side of your battery, or the positive slot in your electrical outlet. The short line denotes the negative side. So the way that a circuit might work is here you have the long side, so this will be the positive side, and then here's your wire coming from the positive side. This wire is attached to one end of a resistor that I'm calling A, and then another wire is attached to the other end, and the other end of that wire is attached to another resistor called B, and then the other end of that resistor is attached to another wire, which is then attached to a resistor C, etc. And then you have a wire going all the way back to the negative end. So the idea is like, okay, maybe you have a 1.5 volt battery. The little knob on your 1.5 volt batteries, the knob is the positive end. So in this case, the knob would be on the left. You'd have a wire coming out from that and then going through a resistor, and then etc., and then another resistor, etc., and third resistor, and then a wire coming back to the negative end, the flat end of your 1.5 volt battery. Now, remember, a resistor could be anything. It could be a toaster oven, it could be a light bulb. Though usually when it's a light bulb, well, I shouldn't say usually, sometimes when it's a light bulb, the resistor symbol is replaced by just a drawing of a light bulb. It's up to you. You can name it either way. But some more terminology here. The way that I have this particular circuit set up is what we call a series circuit. By series, we mean that if you were to follow current coming out of a battery, first it would hit one resistor, then it would hit another resistor, and then it would hit another resistor, etc. And then after that, it would come back to the other end of the battery. That's what we mean by series. Now, what do we mean by following current? So here's the thing. By now, most of you have been through chemistry class, and in chemistry you learned that electrons are what usually carry charge, although in chemical solutions a lot of times positive ions will carry charge as well. But in electric circuits, electrons carry the charge. Now, electrons are negatively charged. That is highly inconvenient because circuit diagrams had been set up long before we discovered electrons and long before we discovered that it was negatively charged particles that actually carry charge. And it was simply assumed that current was the direction of positive charge flow. So by convention, we pretend that there are positive charges coming out of the positive end of this, going toward the left, going clockwise, first through resistor A, then through resistor B, then through resistor C, and then back to the negative end because opposites attract. Of course, you know that in reality it's actually negative charges coming out of the negative end and going counterclockwise, first through resistor C, then through B, then through A. The charges themselves, by the way, move very, very slowly. They move like much slower than typical walking speed. They move like a few millimeters per second. You might wonder, well, wait a second, I thought they move at the speed of light. I mean, you turn on the light switch in your room and the light comes on pretty much immediately. Well, it's the signal that travels at the speed of light. When you turn on the light switch, it sends a signal to each charge to get moving. And as soon as that charge starts moving, it sends a signal to the next charge down the line to get moving. And it keeps doing that, and that signal travels at whatever the speed of light through the material is. Through a typical conductor, the speed of light is maybe about 2/3 what the speed of light is in vacuum. But in any case, yeah, I want to mention those couple of things. But again, for the purposes of the rest of this discussion, we're going to pretend that it's positive charges that are actually carrying the current. It will not make any difference whatsoever from the reality of negative charges flowing in the opposite direction. All of the math is exactly the same. So we're just going to be allergic to negative signs and pretend that it's positive charges carrying the current. It'll keep the equations much simpler so that we don't have to cancel lots of double negatives, because we don't do no double negatives. Anyway, there are resistors that can be in series, like in the last slide, and then resistors can be in parallel. What we mean by parallel, so first of all, instead of having this notation of the battery or source symbol of like that, with the long end here being positive and the short end here being negative, in this situation, what we're saying is that this part right here with the little knob at the top, that's the positive end, and this ground area, this is what we're calling the negative end. Presumably, though, these are connected in some way. We just didn't have room to draw it. But imagine just taking this rectangle and getting rid of these three resistors and inserting this rectangle, like this end being the left end of that previous diagram, this end being the right end of that previous diagram. So kind of rotate that on that slide by 90 degrees counterclockwise and insert that here, get rid of these three resistors and insert the other end here. It would be exactly the same circuit as what you have right here. I just wanted to mention that. But here, these three resistors are what we call in parallel. So remember, in series, first the charge goes through one resistor, then it goes through the next, then it goes to the next, etc. When resistors are in parallel, or anything's in parallel, it's happening all at the same time. You have some conventional charge. When I say conventional charge, I mean positive charge, coming out of here. It hits this, it splits. It has a choice of three different routes to go. It either goes through A, or it goes through B, or it goes through C. So what you have now is a little bit of charge simultaneously going through A and B and C at the same time. We say that that's in parallel. So first this, then this means series. Either this or this means parallel. So these are in parallel. Now, most circuits in the world are more simple than just having one resistor. If you just have one resistor, that's an easy calculation to make. We just did it in our heads when talking about that 60-watt light bulb attached to the 120-volt power source from the house a few slides ago. In truth, though, usually you have more than one resistor, more than one light bulb, more than one thing running from your electrical outlets in a lot of cases, that sort of thing. In that case, what you have to do is you have to calculate the equivalent resistance of your circuit. Here's how that works. In series, the equivalent resistance of a bunch of resistors lined up one after another is just given by adding up the individual resistances. So, remember, those resistances have units of ohms. So let's say that you just had three resistors. Let's go back to this example right here. Let's say the resistor A was 10 ohms, resistor B was 30 ohms, and resistor C was 20 ohms. Well, the equivalent resistance of this whole thing would be 10 plus 30 plus 20 ohms, which would be 60 ohms. Why do we care about equivalent resistances? Because the equivalent resistance of your circuit is what you end up plugging into Ohm's law when trying to figure out how much current is actually going to come out of your battery. Now, Ohm's law is valid for each individual resistor as well. In other words, if your battery has 12 volts, actually, let me just make things nice and round. I'm going to say the battery has 120 volts in this particular example. If this battery has 120 volts and the equivalent resistance here is 60 ohms, that means that 2 amps of current are going to come out of here. V equals IR, so I equals V over R. 120 volts divided by 60 ohms is 2 amps. Well, Ohm's law is also valid for each individual resistor. So if 2 amps of current is coming out of this battery and going through here, well, that's going to be 2 amps going through resistor A. Well, that's 2 amps times its resistance, which I said was 10 ohms. That means the voltage drop across resistor A is 20 volts. So if I was to take a multimeter and turn it to the volt setting, put one terminal of the multimeter on one side of the resistor and the other terminal on the other side, that multimeter should read 20 volts in this case. What about through resistor B? Well, the current can't pile up anywhere. It's 2 amps everywhere in this case. So that's because charge can't be lost, conservation of charge. We're going to get to that soon. But it's still 2 amps here, 2 amps times 30 ohms right here. That's going to be 60 volts voltage drop across resistor B. And then 2 amps times 20 ohms is going to be 40 volts voltage drop across resistor C. And notice, of course, that those add up to 120 volts. That shouldn't be surprising. That's actually something called Kirchhoff's loop rule, which we're going to talk about soon. So yeah, when resistors are in series, you just add them up. So, quick example here. Find the equivalent resistance in this circuit. Make sure to show all your work. So there are your givens. Turns out your answer is 20, not surprisingly, but just showing the work. You have your givens. I gave them names, R1, R2, and R3. I listed the equation for 3 resistors in series. R equivalent is R1 plus R2 plus R3. And you add up the numbers, and sure enough, you end up getting 20 ohms. So there's your answer there. What if they're in parallel? So this is an equation that if we had more time in class and stuff like that, we would actually derive this equation. This is an equation that can be derived. It comes from the fact that when resistors are in parallel, each branch has the same voltage drop. Each branch has the same voltage drop. It's the currents that split up. Whereas when resistors are in series, the current is the same everywhere, but each resistor might have a different voltage drop. But when they're in parallel, it's like, hey, they're all going down the same distance, so to speak. You always have to start at the positive end and end at the negative end. It's just they're taking different routes to do that, but the voltage is the difference between the positive end and the negative end. So they're taking different routes, but in the end, they've gone from the same point A to the same point B. But anyway, this formula can be derived. The equivalent resistance for resistors in parallel is given such that the inverse of that result is equal to the sum of the inverses. Let's see how that works. Let's say you have a 6 ohm resistor and a 3 ohm resistor. Well, first of all, you should absolutely not add them up and take the inverse. There's a big mathematical problem with doing that. In other words, 1 over A plus B is not 1 over A plus 1 over B. A plus B over 1 is the same thing as A over 1 plus B over 1, or A plus B quantity over 3 is the same thing as A over 3 plus B over 3. But 3 over A plus B is not 3 over A plus 3 over B. That doesn't work. So anyway, if you have a 6 ohm resistor in parallel with a 3 ohm resistor, the equivalent resistance is not 1/9 of an ohm. It's not 9 ohms either. You have to use the formula. So you'd use 1 over the equivalent resistance is 1 over 3 ohms plus 1 over 6 ohms. Common denominator here. The common denominator between 3 and 6 is 6. So you turn that 1 over 3 into 2 over 6. Now you have the same denominator. Now you can add up the numerators. 2 plus 1 is 3. That's 3 over 6 ohms, which is the same thing as 1 over 2 ohms. So if 1 over the equivalent resistance is 1 over 2 ohms, that means the equivalent resistance itself, just flip both sides, is 2 ohms. Now, what about this situation? Calculate this equivalent resistance. So here we're saying that this right here is 10 volts, this right here is 0. So you could just imagine taking a big wire in here, a wire over here, and then put your battery symbol somewhere right here with the left side like that, with the long end. In any case, we have 4 resistors in parallel here. Notice that just because we say that they're in parallel doesn't mean that they're necessarily going to be drawn in parallel. Like in parallel means that things are happening at the same time. It does not mean parallel like from Euclidean geometry. You can sometimes draw things as though they are parallel in Euclidean geometry when they actually are in parallel, but just be careful because that can be a misnomer. For example, going back to our series resistor over here, I could have put resistor A down here, and I could have put resistor C over here. Oh, A in parallel to C? No, these would still be in series. Where I decide to bend my wires does not affect whether they're in series or parallel, so just keep that in mind. So that's thing is like, yeah, you have a diagonal resistor here, but this 1200 ohm resistor is still in parallel with these other 3. So how do we do this? Well, first of all, we give them names. We write out our equation. 1 over equivalent resistance for parallel is, for 4 in parallel is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. And now we plug in our numbers. And there is a common denominator here. Do you see it? The common denominator is 1200. So I can turn each of these fractions into other fractions such that I have 1200 as the denominator. So 1 over 300 is the same thing as 4 over 1200. 1 over 600 is the same thing as 2 over 1200. 1 over 200 is the same thing as 6 over 1200. So when I do that and add up the numerators, I get 13 over 1200. So 1 over the equivalent resistance is 13 over 1200 ohms. So the equivalent resistance itself, well, I'll just invert both sides, flip both sides. Equivalent resistance itself must be 1200 ohms over 13, which turns out to be 92.3 ohms. So what that tells you is that, first of all, something that you should notice, remember when we had a 6 and a 3 in parallel, we got a 2 ohm equivalent resistance. When we have all 4 of these in parallel, we have a 92.3 ohm equivalent resistance. Notice that the result is always less than any of the individual resistances. That's true in general. Whenever you have 2 resistors in parallel or 2 or more resistors in parallel, the equivalent resistance is less than any of the individual resistances. That should make sense. Think about it this way. If you're traveling on the highway, how's traffic going to flow with less resistance? Is it going to flow with less resistance if you have more lanes opened up or if you have fewer lanes opened up? Of course, you're going to flow with less resistance if there are more lanes opened up. What that means is that more current can go along that highway with more lanes opened up. More cars per unit time, just as electric current is more coulombs per unit time if you increase that. So if you increase the number of paths, that means that more current is able to flow, less equivalent resistance. Now, something that should be noted is that voltage is something that is part of the circuit itself. In other words, it doesn't matter what kinds of resistors or anything you put in there, the battery is going to be the same. Now, when you split paths into parallel, that makes sense because that they have the same voltage drop. Think about it this way. When water splits into 2 paths, like going over a cliff, 2 different waterfalls on a river, well, each cliff has the same height because the water's got to go from the top to the bottom. So either path, the water is going to undergo a height drop that is the same from the beginning to the end. So you're going to have the same voltage drop in each case. Now, more water might go one way than the other way. That would mean more current, but they're still going to have the same voltage drop. That waterfall analogy is actually a perfect analogy. I'm not trying to praise myself or anything like that here. What I mean by perfect is that it is mathematically equivalent in the electrical sense to the mechanical sense. The battery acts like the like lock that would be used to raise the water level in a canal. The waterfall acts like a resistor, and the river itself is like a wire when it's not undergoing any change in height. And as the water goes over a waterfall, it can do work. It either does work in terms of getting itself going faster, or it does work by hitting against some sort of turbines and turning the turbines to generate electric power. So if you need to go over some of this in more detail, then just pause the video, but otherwise I'm going to move on so that we can get into some of the calculations. But yeah, in terms of a pure series circuit, it's like you have a series of waterfalls, one waterfall, then the next waterfall, then the next waterfall. And then for parallel circuits, it's like you have two different waterfalls, but they go over the same cliff. So keep in mind, two sets of rules apply when you're trying to figure out voltage drops and currents through individual resistors. Why would you want to do that? Well, you need to make sure that you're not trying to put too big of a load into that resistor. Otherwise, you might end up getting magic blue smoke coming out of that resistor. That has happened a number of times in labs that I've done in class. So luckily, resistors are cheap, but you need to keep that in mind. So don't put too much current through a resistor. Now, when resistors are, and again, in real life, that resistor might have been a toaster oven. If you'd put too much current through that, it would have fried it, and you would have had to buy a new one. Or even worse, it could have potentially caused a fire. So two main sets of rules. First is that in parallel, the net voltage drops across each branch of a junction is where the wire splits into multiple paths, are always equal. And we're going to see how that applies in calculations soon. So different waterfalls, same cliff. Also in parallel, the sum of the currents after a junction is equal to the current entering the junction. So going back to this situation, if I had, let me just think, how about, let's say that I had a certain, I'll just make something up. I had a certain amount of current going through, let's say 10 amps coming into this junction right here at the top. Well, I haven't done the calculation, but I'm just going to pretend that, I'm going to pretend that, say, 4 amps of that current goes through this 300 ohm resistor. Well, if 4 amps went through the 300 ohm resistor, that means that, well, this has twice as much resistance. That means that only 2 amps went through this. So we'd have 4 plus, so, and if 2 amps went through this, that would mean 1 amp went through this. And if 4 amps went through the 300 ohm resistor, that would actually mean that 6 amps went through the 200 ohm resistor. 4 divided by 3 halves, or sorry, 4 divided by 2/3 is the same thing as 4 times 3 halves, which would end up being 6. So you realize now that my numbers here don't work because the total amount of current here of 6 amps plus 4 amps plus 2 amps plus 1 amp is 13 amps, and I just said that there were like 10 amps coming into here. So, okay, fine. Pretend that there are 13 amps going through here. Well, then in that case, 4 amps would go through here, 2 amps would go through here, 1 amp would go through here, and 6 amps would go through here. And, of course, in order to make that 13 amps work, we would need a different value for the voltage here. But whatever, you get the point. The potential difference across each path is the same, but different amounts of current go in different sections. And the amount of current that goes through there is given by Ohm's law. You know the potential difference, whatever the voltage is here, divided by this equivalent resistance, tells you the current that comes out of the battery, but whatever the voltage here divided by any of the resistances tells you the amount of current that goes along that path. Again, we're going to see some examples with that soon. Now, when things are in series, the sum of the voltage drop across each separate region of a series circuit is equal to the battery's voltage. Or at least it's equal to the voltage drop across the overall section. If it's a pure series circuit, in other words, nothing else in parallel or anything like that, then you add up the voltage drops, you're going to get the battery's voltage. So same cliff, but they all go over either all at once or in little steps. Like you divide the cliff into sections or something like that with the waterfall analogy. And also, in series, the current is always the same in a pure series circuit. That's due to the law of conservation of charge. So now let's turn our attention to circuits that are more like what you're typically going to find in the real world and in labs and stuff like that. Generally, things are not just pure series or pure parallel. Instead, you might have a battery with a wire leading to one resistor, and then the wire leading out of that resistor, and then that wire branches into several sections that lead to different resistors that themselves are in parallel with each other. But then that whole thing would be in series with that first resistor that I mentioned. So here's, first of all, something that we need to practice before analyzing these things. You need to understand something called the junction rule. The junction rule is something that we've already actually discussed, just under, we didn't give it a name, but the fact that the amount of current going into a junction has got to be equal to the total amount of current in each of the areas there. So let's say that you were to put a current meter, you inserted a current meter into this region right here. What would the value read for on that current reader? What would it measure? So this is where you end up using what we call the junction rule. It's actually called Kirchhoff's junction rule, but it simply says that the total amount of current into a junction, and again, a junction is where paths split. Anywhere where paths split, the total amount of current in is equal to the total amount out. So, okay, how much current is going through here? Well, that must be equal to whatever 5.7 amps minus the amount of current that went this way is. Well, what's the amount of current going this way? Well, we don't know. We do know that there's 1.3 amps going up, but that's not the amount of current in this wire. But now we can figure that out, because apparently there's 1.3 amps of current going up, and there's also 8.4 amps of current going this way and then down through the 3 ohm resistor. So that means that the amount of current going through this wire right here must be 8.4 amps plus 1.3 amps, which is 9.7 amps. So if 9.7 amps left over here, and 5.7 amps is coming through this way, that must mean that the current in this section through the 12 ohm resistor must actually be going up. The current through here plus 5.7 amps must be 9.7 amps. So in other words, up here plus into over here equals the amount out over here. Well, so how do you solve for that? 9.7 amps minus 5.7 amps leaves you with the 4 amps that must be going up in this case. So there's 4 amps of current going through this ammeter, and that current is going up. So again, we analyze this in separate parts, and can just kind of go through this. And if you need to kind of pause the video, then you can see those details again, or kind of go back through that section, but we just explained it verbally. So why do we need to be able to do that? We need to be able to do that in order to talk about hybrid circuits. Consider this example. Calculate, first of all, the equivalent resistance in the circuit. Well, what we need to do is recognize what's going on here. This is mainly a series circuit. This is a 10 ohm resistor that is in series with a box. What's the box? Well, the box is a 3 ohm resistor in parallel with a 12 ohm resistor. So here's the idea. We recognize that the equivalent resistance is equal to 10 ohms plus whatever the resistance of the box is. So we're going to call the box A. So the equivalent resistance of our circuit is equal to 10 ohms, that is what I'm calling R1, plus the resistance of A. R1, I labeled my resistors R1, R2, R3. Well, what's the resistance of A? Well, A now is just parallel, that's it. So 1 over the equivalent resistance of A is equal to 1 over R2 plus 1 over R3. Well, those R2s and R3, those are givens. 1 over 3 plus 1 over 12. You might get tempted to say, oh, that's 1 over 4, I know that. It's actually not. 1 over 3 plus 1 over 12 is the same thing as 4 over 12 plus 1 over 12, which is 5 over 12, or 1 over 2.4. So the equivalent resistance itself is 2.4 ohms. So now we know the resistance of A. We can plug that in to our equation up here to get that the equivalent resistance for the whole circuit is 12.4 ohms. Okay, now that we know that, we can figure out the amount of current coming out of the battery. So note that since that's the amount of current coming out of the battery, that's the amount of current going through the 10 ohm resistor. So because we know the amount of current going through the 10 ohm resistor, we know the voltage drop across the 10 ohm resistor. And since we know that the voltage drop across the whole circuit is 5 volts, what we can do is we can say, okay, well, remember conservation of energy? You know how if you start at the top of a cliff and you send something to the bottom of the cliff and then you bring it back up, the total change in energy is 0 because it ended where it started. Well, the same thing works for circuits. If you start at 5 volts, and then you go down to 0, and then you come back up to 5 because there's a battery that gets you back up to 5 here, that means that the total voltage drop in any loop of a circuit must be 0. You gain by the battery, and then you lose every time you go through the resistor. So that's something to keep in mind here. So the remaining voltage drop is that voltage drop across what we're calling A. So in other words, since the battery's voltage was 5 volts, we can say, okay, calculate the current coming out of the battery. Well, the current coming out of the battery is 0.403 amps because the equivalent resistance of the circuit was 12.4 ohms. So 5 volts divided by 12.4 ohms is 0.403 amps. Well, that means that's the amount of current that's going through that 10 ohm resistor because the battery is in series with the 10 ohm resistor. It's like first you get raised to a potential of 5 volts, then you go through the 10 ohm resistor, then you go through the parallel junction, then you go back to 0, and then the battery takes you back up. So since we're calling the 10 ohm resistor resistor 1, that means the voltage drop across resistor 1, the 10 ohm resistor, is equal to the current through it times its resistance, Ohm's law again. Multiply those out. You have the current times the resistance, 4.03 volts. Therefore, the rest of the circuit, which we called A, must have a voltage drop of the battery's voltage minus the voltage through the 10 ohm resistor. Why? Because remember, the 10 ohm resistor is in series with A. So I know now that the voltage drop across A is 0.968 volts. But what was A? Remember, A was the 3 ohm resistor in parallel with the 12 ohm resistor. So these each have the same voltage drop because, again, same cliff, different waterfalls. So same height difference if you're thinking the mechanical analogy. So that means that both the 3 ohm resistor and the 12 ohm resistor have a voltage drop of 0.968 volts. So now that we know the voltage drop across both of those resistors, we can determine the current going through either of them. By Ohm's law, V equals IR, so I equals V over R, the current going through the 3 ohm resistor is equal to the voltage drop through the 3 ohm resistor, which we already know, 0.968 volts, divided by its resistance. What's the resistance of the 3 ohm resistor? What's the color of George Washington's white horse? So that's how we got the 3 ohm resistor. 3 ohms right here for the resistance, and that's 0.323 amps. And the current going through the 12 ohm resistor, remember, we know the voltage drop already because they're in parallel. It's the same as that one. Divided by 12 ohms gives you 0.0806 amps. And, surprise, surprise, if you were to add up these numbers, you would end up getting that 0.403 amps that we got coming in. That was just the junction rule, remember, but it works out. Now let's turn our attention to a hard problem. In this case, unfortunately, I've made this a little bit harder than expected by giving this a 196 volt battery here. But again, we could have simply cut this apart and called the top, like an end over here, 196, and then moved this over somewhere else and called that the ground. 0 volts is what ground means. But here I'm actually showing the battery. So anyway, first of all, let's follow the current. It comes out of the positive terminal here, and then goes through the first 12 ohm resistor, and then boom, it meets a junction. It has a choice. It either goes through this 48 ohm resistor and home, because remember, positive charges are attracted to negative areas, like the negative terminal here, or it goes through the other 12 ohm resistor over here. What happens after that? Well, then it either goes through this 20 ohm resistor and then home. It does not go back through here because that would be going toward a positive end. So it goes, and by the way, wires are assumed to have 0 resistance. So once it gets here, it's like, boom, it immediately hits the negative terminal. Or it goes through the 2 ohm resistor. If it does that, it then goes through the 3 ohm resistor. So what do we have here? We have a 12 ohm resistor in parallel with, we have a 12 ohm resistor in series with a box. Whoops. Well, what's the box? The box is a 48 ohm resistor in parallel with, well, part of a box. Well, what's that part of a box? That part of a box is a 12 ohm resistor in series with a triangle. Well, what's the triangle? The triangle is a 20 ohm resistor in parallel with a right angle. What's the right angle? It's a 2 ohm resistor in series with a 3 ohm resistor. So let's figure out everything we can with this circuit. So just like last time, we're going to break it into parts. So we're going to call the big box, we're going to call that box A. So, well, that's easy. The equivalent resistance of this thing, which I need the equivalent resistance if I'm going to find the current coming through this, but the equivalent resistance of this thing is 12 ohms plus the equivalent resistance of A. So all I need to do is find the resistance of A, and I can then start calculating currents. Well, what is A? A is a 48 ohm resistor that is in parallel with other stuff, which I'm circling here and calling B. So if that's A and the orange circle is B, that means 1 over the resistance of A is 1 over 48 ohms plus 1 over the resistance of B. Well, now all I need to do is find the resistance of B. Okay, well, B is, again, follow the charge. If the charge comes through here, it came from this way. It first hits the 12 ohm resistor, then it hits the triangle. Oh, first this, then this. That smells like series. So apparently the 12 ohm resistance, this 12 ohm resistor is in series with the thing that we've circled in blue that we're calling C. It's in series with the triangle. So the resistance of B is just 12 ohms plus the resistance of C. Well, what is C? C is a 20 ohm resistor, just going back here, which is in parallel with a 2 and a 3 that are in series. Well, we can do that in our heads. What's 2 plus 3? 2 plus 3 is 5. I really hope you weren't reaching for your calculators on that. So what we have is we have a 5 ohm equivalent resistance in parallel with a 20 ohm equivalent resistance. So remember that inverse formula, 1 over the resistance of C now is 1 over 20 ohms plus 1 over 5 ohms. Well, 1 over 5 is the same thing as 4 over 20. And so now we have a common denominator here. So that's 4 plus 1 over 20, which is 5 over 20. 5 over 20 is 1 over 4. So apparently the equivalent resistance of that triangle that we called C is 4 ohms. Again, it's less than any of the parallel paths. This parallel path was 5 ohms. This parallel path was 20 ohms. The equivalent resistance turned out to be 4 ohms. Well, remember that C was in series with this 12 ohm resistor. If this was 4 ohms, if C was 4 ohms and 12 ohms is 12 ohms, well, the resistance of this whole thing right here must be 16 ohms. Well, that whole thing is what we call B. So B's equivalent resistance is 16 ohms. Well, remember, B was in parallel with a 48 ohm resistor. So 1 over the resistance of the big box A, remember A. I hope you remember A. A was this big box right here. So 1 over the resistance of A is 1 over 48 plus 1 over the resistance of B. But now we know the resistance of B. The resistance of B is 16 ohms. So 1 over 48 plus 1 over 16. Well, 1 over 16 is 3 over 48, common denominator again. You get 4 over 48 or 1 over 12. Well, if 1 over the resistance of A is 1 over 12, that means the resistance of A is 12 ohms. Well, remember, that whole big box that we called A was just in series with another resistor, and now we're done with our circuit, because that's it. We had another 12 ohm resistor, so 12 ohms plus the resistance of A is the equivalent resistance of the whole circuit. That's 24 ohms. So that was somewhat complicated, but in the end, we can do it by this nested sequence of steps. Notice this is slide 5 of 10. We're halfway done. Now we need to use this to figure out what kind of current's coming out of the battery. And this is where I wished that I had used 192 volts for my battery, because if this was 192 volts, this would have gone through evenly, because 192 over 24 is exactly 8. Oh well. So anyway, using Ohm's law to find the current coming out of the battery, that turns out 196 volts for the battery divided by the 24 ohm equivalent resistance means that about 8.2 amps is coming out of the battery. Well, what does that 8.2 amps current do? First, it hits a 12 ohm resistor, suffering a 98 volt voltage drop. So multiply the current times that 12 ohm resistor, there's 98 volts. So what does that mean? Since we had a 196 volt battery, and we've already lost 98 volts of it through doing work on that first 12 ohm resistor, that means that there's only 98 volts left for the rest of the circuit that we called that big box A. So the 98 volts goes from here along this path, 98 volts goes from here along this path, and 98 volts goes from here straight across this path. So going from here to here on whichever path you want is going to be a potential difference of 98 volts. That's what we mean here. So what do we do now? Since we know that 98 volts is the potential difference from here to here, and we know the resistance from here to here, it's 48 ohms, it's just that one resistor, that means that the amount of current here, V equals IR, I equals V over R, is 98 volts divided by 48 ohms, is 2.04 amps. Well, we know that there's 2.04 amps of current going this way, but we also know that there were 8.17 amps of current coming out of the battery, going through this resistor and entering this spot right here. So if we know that 2.40 amps of that 8.17 amps is going this way, that means that the amount going this way must be 8.17 minus 2.04 amps, which turns out to be 6.125 amps going this way through this other 12 ohm resistor. Well, what kind of voltage drop goes through that? Well, we know the current going through that. We just got that by subtraction. To get the voltage drop, do V equals IR again. So you have 6.125 amps going through here times 12 ohms gives you a 73.5 voltage drop across this resistor. So if you stuck a multimeter with one positive terminal on this end, the negative terminal on this end, you would get 73.5 volts for the reading on that multimeter. By the way, if you switched which terminals you were putting on which ends, the number would be negative. Anyway, so now we know the voltage drop across this way. Well, we also knew that the voltage drop across B, go back to a previous slide if you've forgotten that, was 98 volts. So if there's 98 volts across all of B, and 73.5 volts is lost across the 12 ohm resistor, that means that there's 98 minus 73.5 equals 24.5 volts left to go across the rest of B. That means 24.5 volts across this 20 ohm resistor here. Ah, I know the resistance of that path. Ah, I know the resistance of this path too. It's 5 ohms. So, first of all, the 24.5 divided by 20 ohms gives me 1.225 amps across this path. So I know the voltage drop and current across this resistor now. And since I know there's 24.5 volts voltage drop across this path, remember it's in parallel, so the voltage with the 20 ohms, so the voltage drop's the same. That means that I know I'd just take 24.5 volts divided by 5 ohms of resistance here, and that would give me 4.9 amps. Another way I can do it is recognize, hey, this is the only path other than this 20 ohm path, so I know the current going into this junction was 6.125 amps, and if I just calculated that 1.225 amps ends up going this way, that means the other path must have the other 4.9 amps. So 4.9 amps of current is going through this path. So finally, we're just about at the end. Notice slide 9 of 10 on this example. 4.9 amps times 2 ohms is 9.8 volt voltage drop over here. 4.9 amps times 3 ohms is 14.7 volt voltage drop across the 3 ohm resistor. So now we're done. We found everything we can in terms of the current going through each resistor and the voltage drop across each resistor. And because of that, we can figure out how much power is being dissipated by each resistor. And that's important again because if you try shoving too much power through that resistor is going to burn up. Resistors are rated for a certain maximum power. If you exceed that maximum power, you risk destroying the resistor, whether it's a resistor, a toaster oven, a television, a computer, or whatever. So keep that in mind. So remember, we have PIV. Now, PIV has multiple forms. So that's just the mnemonic, PIV. The power dissipated by a resistor is equal to the current going through it times the voltage drop across it. We've calculated both of those for each of those resistors, so we could just directly use that equation. But there are other times in life where sometimes you don't already know the voltage drop across the resistor. In that case, you use Ohm's law. Well, V equals IR, plug that in, and you realize that the power dissipated by resistance is equal to I squared R, the square of the current going through it times the resistance. Or sometimes you don't know the current going through a resistor or a light bulb or whatever, but you might know the voltage drop. For example, in household current, if you just plug something into an electrical outlet, boom, you know the voltage drop there. That's 120 volts. So if you know the power of that light bulb, well, if that's a 60-watt light bulb, then we can figure out the resistance that's needed in order to give you a 60-watt light bulb. So you have P equals IV, PIV, but since I is equal to V over R, you plug that in, you have V squared over R. So let's say it's a 60-watt light bulb, and I want to know how much resistance is required to give me a 60-watt light bulb. How much resistance must my tungsten filament have? And based on that, I can figure out the length and cross-sectional area of that. That's a more advanced concept. That's more for an AP physics class, but it's not too difficult even there. It's just a simple formula. But anyway, P equals V squared over R. So if I want to solve for the resistance that's needed to give me a 60-watt light bulb, I would put in 120 volts right here. I would square that. That would end up giving me 14,400. And 14,400 divided by 60, well, I can cancel a factor of 10 there. That would be 1,440 divided by 6. And that ends up being 240 ohms. So a 240 ohm resistor plugged into a, let's see, is that right? Yeah, 1440 divided by 6 is 240. So yeah, 240 ohms would be my equivalent resistance, or sorry, the resistance that I would need for my light bulb there. Now, what that means though is that given you had a 60 ohm resistor there, calculating that power, well, if that light bulb has a maximum power rating of, say, 100 watts, even though it's set to be 60 watts, what that means is if you ended up plugging it into a 240 volt power supply in Europe, suddenly instead of having 60 watts going through there, you would have 240 watts going through there because you've doubled the voltage, which means the power is multiplied by 4, 2 squared there. So that would probably destroy the light bulb, so you got to be careful. Now, in terms of those other resistances, yeah, you could have calculated the current, or sorry, the power dissipated by any of those resistances that we got now that we know current and voltage drop across all of them. So in this other example with household current, let's see what kind of current would be going through a 75-watt light bulb that is plugged into an electrical outlet, or a lamp that's plugged into an electrical outlet. So P equals IV, that would be 0.625 amps. So now finally, what about your typical bright 100-watt light bulb? What would its resistance be? So remember, that's assuming that it's running from standard household electrical current. So we have P equals 100 watts, so the voltage is 120 volts. Well, we have P equals V squared over R, because remember, we know the voltage, we know the power, we don't know the resistance, but we don't know the current, so we can't use PIV, and we can't use P equals I squared R, but we can use P equals V squared over R. And when we plug in our numbers, first solve for R, so that's R equals V squared over P, so multiply both sides, take the original P equals V squared over R, multiply both sides by R, divide both sides by P, you get R equals V squared over P, plug in your numbers, and you get 144 ohms for the resistance that would be necessary in order to give you a 100-watt light bulb. Now, in that previous example that I gave, remember I said that 240 ohms would be necessary for a 60-watt light bulb. So in other words, yeah, you decrease the resistance, you're going to increase the power that's being dissipated there because you're increasing the current, and that ends up heating it up a lot more quickly. So something to keep in mind. If you decrease that resistance, you risk burning things out as well. So that is a lot of resistance. In fact, it's so high because of the relatively high voltage of that power source. But yeah, if you were to plug it into that same bulb into a 240 volt socket in Europe, yeah, it would be 4 times as bright because of the fact that you have that P equals V squared over R, and it's the V that's fixed, and the R is fixed. Well, the V is what you're changing, and the R is fixed. So, again, just something to keep in mind. Now, there is a YouTube video showing how people who are MIT graduates supposedly cannot use a battery and a wire to light up a light bulb. So it's like, oh, they graduate from MIT, but they can't light up a light bulb. Well, here's the thing. They're giving people a normal 1.5 volt battery, but they're giving them a 100 watt light bulb. So even when they do the experiment correctly, just plug those numbers into the equation, that supposedly 100 watt light bulb, which we just calculated has a resistance of 144 ohms, if you only plug it into a power source that's 1.5 volts, which is what your handheld battery is, the wattage on that is going to be 0.0156 watts. So yeah, it actually does light up, but that's so dim you're not going to be able to see it. Unless maybe you put it in a very, very dark room, but I don't even know whether your eyes would be receptive to that even in a perfectly dark room. So that's something to keep in mind, just common misconceptions on those types of things. In truth, yeah, most MIT graduates can light up a real light bulb. Usually when this type of experiment is done with a battery, you use a much, much smaller light bulb. So that's the end of our discussion about circuits. I hope everybody found this somewhat informative, and if you're confused, maybe go back through it, and if you're still confused, then post your questions in the comments section. Otherwise, thank you for watching, and have a good day.